Hello, I'm Nanix, and this is part 3 of the Let's Make a Survivor tutorial series. In this part, we will be implementing a finite state machine and creating our first enemy. To begin, we will duplicate the player, call it enemy, so that it has the same setup as our player object. We'll then remove the player script, as this will be the enemy, and we do not want to register this as the shared transform for the player. We'll move the player back to the middle of the world by setting it to 0, 0, 0. We'll grab the enemy and we'll set them, let's say 10 on the X and 10 on the Z, so they start in the corner. And to differentiate the two, I will rename body to player, duplicate it with Ctrl D, and then rename this one to enemy, and we'll make it a nice enemy flavored color. About there. Then dragging and dropping that onto the enemy. Now, we're going to add a script to our enemy that controls their movement and their look rotation, as well as handling the logic behind their finite state machine. This will be done using a mono behavior called enemy. Open that up. We'll remove the start and the update, as we won't be using those for the moment. We're going to first create the overview of the system. To begin, we need movement and looking, very similar to how the player works. So we'll grab those two functions from the player script. That's player.cs directly below it, and paste those into the enemy script. It'll throw a bunch of warnings because we've got variables that haven't been defined. We'll grab these variables from up here at the settings, and we'll paste those in at the top of the enemy script. Do not forget the private ones here. Excellent. We also then need to grab the awake function, as that is where we're registering the rigid body component to the variable RB. Can't forget to do that. And now we just need to make a few changes here. For starters, we won't have a move input. What we will have instead is a vector3 argument that's passed through on move called direction. And we'll set this here from move input to direction. We'll do the same thing with the look function as well, by copying this argument, pasting it here, and then replacing move input with direction. Excellent. Now we'll go over a very basic implementation of a finite state machine using a switch case setup. To begin, we need to create a public enum. We'll call it state, and in it we'll provide the basic states. So idle, chase, telegraph, attack, and cooldown. And to handle the states, we'll create a public variable of type state called current state. Then we'll create a fixed update loop, and within here we'll create a switch case statement to handle how we want the states to function. If you're using Visual Studio Basic, you should be able to type in switch, which is the function, press enter, press tab, and then type in current state, which was the variable we set up here. Press enter, and it will generate a default set of whatever the enums we've set up here are. It's a very basic way to do it. Then we would have each of these states. So in idle we would do nothing. In chase we will chase the target. In telegraph we will telegraph the attack. In attack we would do the attack. And then finally in cooldown we will activate the attack cooldown. Now that we have all this separated out, we can start creating the logic. Since we generally wouldn't have an idle state for this specific game, I'll actually just remove that. So the enemy will just start in the chase state. And within the chase state, we need to get a direction from our enemy to our player. To do so, we will add a new header. We'll call this one shared, like we have with the other scripts. We'll add the serialized field private of type shared transform, and we'll call this underscore target. The reason we're doing that is we'll then add a private transform field, which we'll call target, using the shorthand version of the getter to return target.shared. This means that the variable target in this script will access target shared. Again, this is the same as doing private transform. We'll just call this a target. And then setting up a getter that returns target.shared. Exactly the same thing, just shorthand. So with that, we can now get our distance, direction, and all of those other wonderful things. We'll create a vector3 called vector. We'll make it equal to our target.position, which is the 2, minus our current transform.position. We don't want to normalize that just yet. Now we have a vector that is aligned from the current transform, so this object, to the target. Always remember it is to and then from. From this, we can then get a direction, which is vector3 direction equals to vector.normalized, and we can get a distance, which is vector dot, and we'll use square magnitude because it's less process intensive. Cool. Now what we're going to do here is we're going to move to the direction, and we also want to look at the direction. And now we need to add a little bit more logic based on which state the enemy is in. We'll do that up here. We'll create a header, and we'll call this one state chase, and we'll just repeat that: telegraph, attack, and cooldown, telegraph, attack, and cooldown. Within each of these, we can set up the individual state settings. So we'll create a serialized field, private, float, and we'll call this chase distance, and we'll set it equal to 25. In telegraph, we'll just copy this line from up here so that we can do this quickly. We'll create another float. We'll call this one telegraph time, and we'll set it to 1 second, or 1F. In attack, normally we would do something like damage in here, but the system will probably throw a tantrum because we're not using that. So just for the moment, we'll comment that section out. And in cooldown, we'll have the cooldown time equal 1 second as well. Okay, now that we've got a few of these variables up here, we can start adding transition information into these states. So what we want to say is, if the distance between the enemy and the player is less than or equal to the chase distance, or rather it should be called attack distance, but we'll call it chase distance here, then we want to change our current state into state.telegraph so that the enemy begins telegraphing their attack. We also, at this moment, the way that this is set up, need to create some sort of time check for this telegraph state. So we'll create another variable, just for now, up here, and we'll call it private float state time. And we'll set state time equal to, we'll just do it this way, time.time plus telegraph time. Okay, makes it easy. We don't have to add a cooldown counter inside of the loop. We can just set a time and check that. We can now move on to our telegraph. And if I had it, we would have some sort of effect that grows out maybe a target line of what the attack damage range would be from the character until the end when the attack fires. For now though, we'll just check instead if time.time is greater than or equal to state time, then we want to trigger our attack. So we go current state equals state.attack. So after the timeout here of the telegraph time, we want to then switch into the attack state. If we then had this set up, we would create maybe a hurt box that appears for 1 frame, trigger that here, and then immediately we want to set our current state equal to state.cooldown. And within the cooldown, we need to do the same thing. So we'll set the state time to time.time plus cooldown time. And then inside of the cooldown, we can add, if the time is greater than the state time, so what we're waiting for here, then we want to switch back to the chase state. Excellent. Because we're using rigid bodies and they've got constant acceleration and velocity, we need to add a few extra little parts here. We're going to make a method called hold, and within hold we want it to pass through move with a vector3.0 as the input. Then in each of the states where we should be holding our position, we'll run that hold function. So telegraph, attack, and cooldown. We should also add some extra logic up here into the chase segment, but I'll show you why in a second. First of all, we want to go save, jump back over to the project, find our enemy, grab the script we just made, and drag it onto the enemy. We then need to set the shared transform to player 1, as we had done that test before, and I want to change the move speed of this character to 8, so that it's slower than the player, who moves at 12. Which gives the player a little bit more of a chance. Chase distance is 25, telegraph is 1, and cooldown is 1. Excellent. If I hit play now, we should immediately see the enemy moving towards the player. And then they're entering attack, cooling down, and then attacking again. Now here's why I said I need to add a little bit more logic. You can see here that the enemy's not turning towards me. It looks like it starts to turn, but then immediately transitions again to the telegraph state. So we'll add a little bit of logic in that allows them to actually turn towards the player before triggering that state. It's just a simple little bit of logic. And to do that, we'll be using the function vector3.dot, which gives us a dot product between two vectors, as the little helpful pop-up there says. And the two vectors we're looking for is direction, which has been normalized, and our transform dot forward, which is the direction of this vector here. So wherever the enemy is facing is their forward vector. As with dot products, the closer that angle A is to angle B, the closer to 1 you are. So we can add an extra bit of logic here that says, and we need to set this to a variable first actually. We'll call it facing, and we'll just move it up here so that it's with the other block of content. We'll say if facing is greater than or equal to some variation, about 10% towards a direction. We can't set it to 1 because this is a float and it will barely ever reach 1, but by setting it to something greater than or equal to 0.9, we should get the effect we're looking for. At the same time, we want to limit the movement of the player. Otherwise, I'll show you an example. If the facing is not accurate, the character will keep trying to move towards the player, which will give us that strange effect, where they sort of run into you like a lunatic. To limit this, all we need to do is add a conditional here that says if the distance from the player to the enemy is greater than our chase distance, then we move. Jump back over to the editor, hit play, and you'll now see how we want this working. The enemy comes towards the player, prepares its attack, and then fires. Then it re-angles itself. As I'm still within the attack range, it's going to keep trying to spin and attack me. If I move out of the range, it'll keep chasing me. And it is now working through states. So we'll stop that. And now there are a few things that need to be cleaned up. In our look, we want to actually set the angular velocity of the rigid body. Angular velocity to vector3.0. This is to stop them from spinning non-stop when they're not actually performing the look action. We'll do the same thing for the player, in fact, as I just noticed it before whilst doing that test. That should stop them from spinning on the spot when they interact with each other. But now we're going to move all of this into an interesting format of the finite state machine. This is a basic state machine here. You could just leave this and run with it for the rest of the game, but I enjoy making things more modular, more expandable, and simpler to use in future iterations or requirements. To do this, we're going to move all of these states here into their own functions. Okay, now that we've done that, we're going to remove this block of content here. We're going to remove the idea of the enum state and its current setting. And instead, we're going to save that, jump back over to the editor, see that there's a bunch of errors now, that's fine. We're going to create a folder, we'll call it core, and inside there, we're going to create a script that is just an empty C# script called State Machine. Now, this implementation has been inspired by a developer known as Firebelly Games. Theirs is for Godot, and it's called the Callable State Machine. I really like how they've done this, so I've ported it over to Unity. To begin, we need to create a public delegate, void, callable. What a delegate is it's a reference to a function. So we can set callable to a function, and then whenever we use callable inside of another method, it actually calls the function we've assigned to it. It'll make sense in a minute. We then need to create an extra state, which we're using as a container called class state, which has a public callable update, public callable enter, and public callable exit. The IDE has just seen that. We then need to create a constructor for this, which has callable update, callable enter, and callable exit. Correct. The autocomplete has allowed me to just quickly do that. Wonderful boilerplating. Over in the state machine class itself, we need to create a private dictionary that takes a string for the key and a state for the value. And we'll call this states. We must initialize it as well. Then we need to add a public string that holds our current state. Now to create the overview of functionality. We want a public function called addState, and in that state we wanted to pass in the update, enter, and exit callables. We'll finish that one out in a moment. We then need one for initializing the state, so initial state, and that should take a callable with the name of state. We then need a function called change state, passing in callable with the name of state. We need a function called set state, which takes a string, call this state name. And finally, we need a function called update, which is what the loop will do when it is run in the update. To begin, we're going to register the states when this function is called. And to do so, we're going to create a state called new state, and we'll set it to new state using this constructor we've got up here, passing in update, enter, and exit, and then adding that to the dictionary using update.method.name to get the string of the first function that we've passed through, and this new state variable. In initial state, we just want to call change state and pass through the state, keeping true to the dry type of programming. Don't repeat yourself. Inside of change state, we then need to grab a string called state name from the state that's been passed through using state.method.name. We can then ask if states contains that key of that name. If you remember, we're using a string as the key and state as the value. We want to set state to that state name because it's a valid option. Inside of set state, we're then going to do our logic, which enters and exits the states. So if there is a current state, so if current state is not equal to null, and the state's current state, accessing it using the string as a key that's currently existing, dot exit is not equal to null, then we want to call states current state dot exit as a function. This will call the callable function that has been assigned to exit. We then want to set our current state to state name, which has been passed through, and since we're entering a state, we want to say if current state, we'll just for sanity check to make sure it's not null. It never should be, but it could be. Then we check if the state's current state dot enter is not equal to null, and if both of those are true, then we want to run that enter function. Similarly to that, inside of update, we want to say if the current state is not equal to null, always sanity checking, and the state's current state dot update is not equal to null, then we want to run state's current state update. Wonderful. And that is the callable state machine recreated in Unity from Godot. Let's make use of this now. Jump back over to our enemy script. We want to create a private state machine called state machine, and we want to initialize that here in our awake function. So we set state machine to equal a new state machine, and then we need to run through and add our states. We can do that by setting add state. Now it's looking for the function that will run during update, the function that we enter with, and the function we exit the state with. So simply enough, we want our chase state. It doesn't have an entry and it doesn't have an exit. so we can just send through null, and then we'll just duplicate that for each of these other states. So chase, telegraph, attack, cooldown. And we'll set those, attack, and cooldown. Now, where we've got this logic happening, setting the state time, we want to do that as we exit or enter states. For example here, we're going to create a function called enterTelegraph, and within that, we want to set the state time equal to time.time plus telegraph time. Then we can go up here and add enterTelegraph as the enter function here. So now when we're entering the telegraph state, we're going to set the state time checker to this, which then allows our telegraph function to know that once it reaches that, it can move to the next state. We'll do the same thing with our cooldown. And this breaks things up and allows us to have differing logic based on entering and exiting states. Keeping things clean. Very similarly, we'll grab that from attack and move it into here. Now we need to update these calls here, as this was for the old setup. We want to do state machine dot change state and then pass through the function that is going to be called, so telegraph. And we'll just go through and clean up these other ones. So this one should be attack, this one should be cooldown, and this one should be chase. Wonderful. Now within our fixed update loop, we just want to call state machine dot update. And everything will be handled by that new script that we created over here called state machine now. One thing we did forget to do though is, and I will do this for sanity, we'll create the start function and we'll go state machine dot initial state and we'll set it to chase. We don't have an enter state for chase, but if we did, when you use initial state, it runs change state, which checks to see if the state exists in our list of states, and if it does, it then calls set state, which would run the exit function of the existing state, which is null, so it doesn't call that. But then once it enters chase, it would then immediately run the chase enter state. We'll save this script, then jump back over to the editor, make sure all the settings are right, hit play, and we're now using the wonderful new callable state machine. Still handling all the same processes, just divided up and more modular. If we wanted to see what the enemy was doing inside of its brain, we could pass through a debug.log in this setState function and just say changing to the current state, so state name. And then when we play, you can currently see what state it's entering. Chase, telegraph, attack, cooldown, in that order. And there we have our first enemy type, the Chaser, using a finite state machine to handle its various states, functions, and logic. If you find this interesting and want to follow along, please subscribe to my channel. If you have any questions, queries, or feedback, please head to the comments section and reach out. Thank you for watching.